Hello, this is Mark Haas, and this is my presentation, Advances Toward Space Elevator Tethers. So first and foremost, hello everyone. I'm sorry I can't be there in person. Before I begin, I'd like to tell you a little bit about myself. I'm an adjunct professor at the University of Cincinnati. I'm teaching there while I finish up my PhD dissertation. Now, that dissertation, and most of my research over the last 5 or 10 years, has been researching the structure of carbon nanotube materials, as well as how we can synthesize nanotubes, how we can make materials out of them, how we can make sensors and devices, that sort of thing. These days, most of my research is on nanoscale tomography, kind of like a CT scan, but for molecules. That structure of how these molecules combine to form threads and sheets and our macro scale materials turns out to be absolutely critical for the properties of those materials. And so I've been looking into the relationship between those, with a special focus on carbon nanotube materials, though the work is applicable in a few other areas as well. As far as the presentation today, we're going to take a look at what a space elevator tether and the material it's made of need to accomplish. We'll then look at what materials exist or will exist in the very near future that could accomplish this goal. We'll consider what shape those options will take, how those materials or materiel might come together in order to make this tether. And then finally, I'm going to do a little speculation and try and predict when this tether material will be available, both in terms of quantity and in terms of properties for our use. So starting with the space elevator, most of what I'm going to be talking about today, when I refer to the space elevator, what I mean is this more or less classic design. About 100,000 kilometer ribbon, give or take, depending on how you design it. The center of mass for this ribbon is at geosynchronous orbit, and then powered cars, remotely powered cars, move up and down the elevator cable, dropping off payloads at various positions so that those can be either inserted into low orbit around the Earth, moved into a geosync slot, or be thrown from Earth's orbit towards some other solar system body. The remotely powered is key for this design, otherwise the cars end up being too heavy. We don't have much of a practical application there, but we're going to focus on the tether. Now, the environment for this tether is equally important. Below geosync, we have a couple of radiation belts, which are going to interfere, or at least interact with our tether. We also have to worry about an ozone, just above the surface of the Earth. A lot of materials react quite readily with ozone and other reactive oxides. So ozone here is going to be a shorthand for lots of very reactive chemical species in the upper atmosphere. And then at all levels, we're going to have issues with either micrometeoroids, space debris, or both. So that's the environment our material has to survive in, and that's the rough design it needs to achieve. Now, obviously, I'm leaving out a lot of detail here. Right now, we still don't have enough advances in materials, in policy, in design to get too much more detailed than this. Having said that, that work is occurring, and so I expect to be revisiting this several times over the next few years. So, let's consider this environment and what our material needs to accomplish within that. First and foremost, it has to have a high specific strength. Probably one of the highest specific strengths of any material we've ever created. If we don't have that strength, we can't deploy the tether in the first place. It will tear apart. So strength is critical. I say specific strength here. For those who aren't familiar, that means the strength of the material divided by its density. We cover a wide enough range of positions above the Earth that variation in gravity, and thus variation in density, might actually be relatively important. So we're looking for something that has good strength per weight, not just good strength in the absolute. We'd like something that's chemically stable. We've got that ozone layer to worry about, where we'll have reactive oxides. Above that, while the atmosphere is much, much thinner, trailing on to barely existent. What chemicals there are very reactive, and our radiation belts promote reaction, so we have to be concerned about that as well. The belts don't just promote reaction, though. The radiation that is contained therein can damage chemical bonds, degrade materials, and overall limit the performance, either in terms of life or properties, of any material we might deploy. Above and beyond these basic material considerations, we also have an operational consideration. Whatever tether we deploy needs to be able to be repaired and maintained while deployed. If we start noticing damage in one region or the other, ideally we don't want to have to shut down the space elevator, reel it back into geosynchronous, deal with the problem there, and then reel it back out. That's a long deployment. There's a lot that can go wrong there. We'd like to be able to maintain it in its active position and repair it in that active position, if at all possible. On the last one, dealing with this material, an industrially viable production method. I say this because I'm going to make a couple of assumptions. The first assumption, the tether material will be made on Earth. Now, I might be wrong there. Maybe we'll have some advances in on-orbit factories and it will make sense to synthesize our material up there. But in either instance, we still need a material that can be produced in large quantities and that is available in large quantities and in high quality. Whether it's made on orbit, made on Earth, and taken to orbit, or some hybrid of the two, we're not going to do this project with 5 pounds of material. We'll need tons of material, and that's just for testing and the seed ribbon. As we build up, as we deploy more ribbons, mass could very easily increase, and this is assuming the highest tensile strength available. If we have to work with a little less than ideal strength, our mass per ribbon could easily go up into the thousands of tons. Strength, of course, is the most important of these properties. Industrially viable is actually probably number 2, because if we've got the strength but can't produce it, it doesn't matter too much. Outside of that, we want something that's easy to repair and chemically stable and radiation resistant. But if the material itself is not innately those things, there are engineering techniques that we can use to deal with that, to protect against radiation damage rather than rely on the material to resist it, to protect against chemical attack, to make it more maintainable, more repairable. These have significant costs in terms of weight of the ribbon, dollars or euros to deploy, things like that, but those become engineering decisions rather than fundamental science ones. I'd much rather have to deal with problems of, does it make more sense to have it cost a little bit more and easier to maintain versus the reverse, rather than still struggling to make the material in the first place. So let's be honest, that's a fairly tall order. Are there any materials that can accomplish this right now? Well, we do have a few. But let's broaden our consideration to a lot of materials. All of them, in fact. Now, what we're looking at here is the skeleton of what's called an Ashby plot. A classic engineering technique where you have some set of material properties that you care about. In our case, tensile strength and density. And so you're going to take as many known materials as you can find, plot them on these axes, tensile strength and density, and then you can define criteria which mean that the material is meeting your needs. In our case, that's these tie lines here, which I'll explain momentarily. Anything that exceeds your needs enters into the values, the materials for consideration. Anything that doesn't can be excluded. Now, we don't just do this for tensile strength and density. We see this for all manner of properties, more or less any pair you can come up with. We could be talking conductivity and density again. We could be talking conductivity and compressive strength. We could be talking tensile strength and compressive strength. There's a balance there, which you often see in civil engineering design. But for our purposes, tensile strength and density. And the three criteria we've got, the lowest line in green is what I'm calling the aramid line. And this line is 4 gigapascals per gram per cubic centimeter. Roughly on par with the strongest conventional commercially available materials, polyaramid fibers. You might know that as Spectra, Xylon, certain forms of Kevlar, that sort of thing. That's more or less the best that we can do industrially by the ton today. Now that's not going to be enough, but if we can't at least meet that benchmark, then our material probably isn't going to be able to make it to space elevator criteria. After that, I've got a second boundary, that middle one in purple. That's what I call my plausible line. Roughly speaking, the plausible line is when the tether for the elevator weighs about as much as everything humanity has put into orbit, from Sputnik on, put together. Now, obviously this is at best a crude metric. There's lots of questions about the design of the elevator that might affect that mass. There's a lot of debate to be had about how much of what we've put up into space counts as having gone to orbit. This is just meant to be a rough ballpark for we've done something similar to this as a species before. It is achievable, but not necessarily practical. And so I find that's right around 20 gigapascals per gram per cubic centimeter. At that point, you have an incredibly heavy space elevator, but the mass of that elevator is comparable to what we've put into orbit in the past. Maybe not practical, but definitely plausible. Anything above that starts to look pretty good. And I've got this one other case, which I'm simply calling my best case scenario, and that's at 50 gigapascals per gram per cubic centimeter. At that point, I think that's about the best that known materials as well as near-term research materials are going to achieve. That assumes some of the highest tensile strength we've ever observed, as well as some of the lower densities. Not the lowest by far, but the highest strength and the lowest density pairs that we've seen. Alright, so that's our basic chart. Let's put some material on it. Conventional materials, in a nutshell. Wood and wood products have a very low density, but their tensile strength isn't great, so we are definitely not making our space elevator out of oak. I don't think anyone of us expected to make it out of oak, but you can see we can quickly eliminate some possibilities. We can also eliminate metals and most alloys. While their tensile strength is higher, getting up to the 2 or 3 gigapascal range, their density is just too high, and so our strength per density ratio insufficient. Metal just isn't going to get the job done. Ceramic and glass won't do the job. Rubber won't. Most polymers are out, with the exception of the aforementioned aramids, which make up that line. Composites, however, do start edging above our minimums criteria. Now, this isn't too surprising, or at least not to me. Some of the strongest materials we know of, and some of the best strength-to-weight ratios we've seen, are in composites. Polymer composites, involving those aramids we've been talking about, fiberglass composites, involving epoxies, other carbonaceous polymer composites. These are more or less at the cutting edge of materials in the strength-to-weight category. That's why we see them in aerospace, on satellites, on new planes, in military applications. So we're going to be looking for some kind of lightweight composite. Unfortunately, none of our conventional materials have reached our plausible threshold. So I'm afraid we're going to have to leave industry and head to the lab to find anything there. And we find 3 things to add when we move back into the lab space. Right at the top, very near our best case line, we find carbon nanotubes. Now, this shouldn't be surprising. We've talked about using nanotubes for space elevators for almost 20 years now. And that's because they have more or less the highest tensile strength ever observed by human beings. That's really all there is to say. Further, they tend to have a low density. You find that about 1 gram per cubic centimeter, which is comparable to water. So they're really at a nice sweet spot with a low density, very high tensile strength. And for the record there, the numbers I'm using on this plot, none of these are theory. These are all empirical, tested measurements. Someone made this material and put it on a tensile testing machine. They weighed it, they measured it, and that's how we got these numbers. There are some pure theory stuff that exceed this, but this is all real data, all real materials. A little bit below carbon nanotubes, but still well past our plausible line, we find boron nitride nanotubes. They're a bit more like a ceramic in terms of their chemistry, but as we'll see, they behave a lot like carbon nanotubes in terms of their structure and strength. So while not quite as strong, they have about the same density and are still quite strong, and so are a good candidate. But that's all molecules. If we get above the molecular scale, the only thing even close is carbon nanotube threads. That's exactly what it sounds like. It's little threads, just like you might weave a shirt out of or use to sew something together, made from carbon nanotubes. Now there's a number of different ways of making these, but the best results in the literature are right at or a little bit above our error midline. So my big takeaway from that is that while we do have some molecules that can get the job done, bridging the distance from the molecular scale up to the macro scale still needs some work. But we are already seeing good results, and we can hope for good results in the future. And we can hope to drive those good results up higher. So, let's take a look at those materials a little bit more closely. First off, nanotubes. My personal favorite, but again, I research nanotubes, so I've got a little bit of a bias here. The highest tensile strength of any known material, 50 to 100 gigapascals, depending on whether it's an engineer or a physicist doing the measurement. That's not a joke, actually. Engineers will use the entire cross-sectional area of the nanotube, so the circle, for their tensile strength, whereas physicists tend to use the area of just the walls, the load-bearing component. So they use an annulus, hollow center. Tends to lead to higher results, depending on your application, depending on your design. As long as you know which one you're dealing with, they're both okay to use. I stick with the engineering one because I'm an engineer and we're doing some engineering. So, I'm going to say right around 50 GPa. Varies a little bit depending on the diameter of the tube and the number of walls it has, but 50 GPa. That's 20 times stronger than the best steels, so pretty good. Density is on the order of 1 to 2 grams per cubic centimeter. Again, that's about the density of water or twice the density of water. About 1/5 to 1/10 the density of most metals. So great strength to weight combination. And they also have a few other interesting properties. The conductivity of a nanotube is variable. Some tubes conduct as if they were metals, others as if they were semiconductors. And you can change the conductivity of any given tube by compressing it, by squeezing it. The reason I find this very interesting for our application is it means nanotubes can act as force sensors. So we could integrate a sensor structure into our tether that would be able to determine what tensile load it was on, what kind of lateral pressure it was experiencing, whether there's been an impact or sustained damage, and those sensors would themselves be load-bearing materials. There's already been some interesting work done with that for aerospace applications and composites, and I see no reason it couldn't be adapted to a space elevator type application. The other thing they've got going for them is that they're reasonably chemically stable. They don't start oxidizing till around 600, 650 degrees C. They more or less don't react with most acids and superacids, and you have to be fairly aggressive in terms of your chemistry, even if dealing with plasmas, to get them to react. They also show a self-healing mechanism. If you've got them in an inert environment and raise the temperature, maybe in the presence of a little bit of carbon, any defects in the structure will spontaneously heal, either by bond rearrangement or by incorporating that extra carbon. They do have one weakness, though, chemically speaking, and that's ozone and oxidation. While they don't start oxidizing or start burning until those high temperatures we just mentioned, they also don't have a stable oxide. Now, what this means is, as nanotubes oxidize, they lose mass and they gain defects. And this isn't true for all materials. Aluminum is a classic counterexample. It too oxidizes, and in the case of aluminum, incredibly readily. But that oxide layer is a stable solid and prevents further oxidation of the bulk structure. With nanotubes, we don't have that. Oxidation just means damage and mass loss. It does not hinder further oxidation. So while it takes an aggressive environment to cause that oxidation to happen, once it starts, unless the environmental conditions change, it won't stop. If we're talking about carbon nanotubes, we also need to talk about graphene. Theoretically, it has a very high in-plane strength. So if you grab two edges and tried to pull them apart, comparable to what we'd expect for nanotubes. Unfortunately, I haven't seen anyone who actually did a practical measurement of the tensile strength of graphene yet, so all we have is theory. Further, the graphene flakes and sheets, they're very flexible. Now, for some things, this is very good. They're excellent for high surface area materials, battery components, conductors, things like that. And they have a great conductivity and some variation in their resistance and capacitive behavior. That's why they're being considered as a replacement for the indium tin oxide in touch screens. But their high flexibility and the need to find a way to anchor all of these different flakes to each other lead me to some questions about whether it's practical to make a load-bearing material out of graphene. The theory looks very good, but the engineering is a long way from happening. Because if nothing else, we haven't even made the strength measurement yet, let alone tried to apply it. Chemically speaking, they're about as reactive as CNTs. No one's demonstrated the self-healing mechanism, but I wouldn't be surprised if one was found. So, very, very comparable, which makes sense. They're both structures that consist entirely of carbon. The vast majority of that carbon is in these six-membered rings. Each of these rings is all double bonds. So, high electron mobility, strong bond, same material, a little different geometry. And that leads to some surprising differences in properties. We'll come back to graphene. It's got some possibilities, but it's got a long way to go. The other one to talk about is boron nitride, which we just mentioned. They have a very similar structure to carbon nanotubes, where you've got these six-membered rings, cages of them wrapped into tubes. In this case, though, we have two atoms alternating, boron and nitrogen. They average out to the same mass as carbon, and the bond length is similar. So boron nitride has roughly the same density as carbon nanotubes. The strength is a little bit less, about 30 GPa, so not amazing, but boron nitride is a relatively new material, and theoretically, it should be comparable to nanotubes in terms of strength. So this may simply represent the earlier phase of research we're in. Beyond that, though, there are some very important differences when compared to nanotubes. While boron nitride is very, very stable chemically, it's much more stable than nanotubes, its stability goes above and beyond. It doesn't really have any oxidation behavior, let alone any oxide issues or oxide losses. And you see the same thing with reactions with strong acids, strong bases. Boron nitride is not inert by any stretch of the imagination, but the things you have to do to get it to react are incredibly aggressive, chemically speaking. So it's incredibly stable. It's also an insulator. Where nanotubes conduct, boron nitride resists. This leads to a nice, interesting parallel with our nanotube, and could give us some useful changes in electrical behavior, that might be important at various positions along the length of the ribbon. Importantly, boron nitride nanotubes are also radiation resistant. So while nanotubes have been shown to be able to heal from damage, boron nitride will do a lot better about resisting that damage in the first place. So, trade-offs. But while different from carbon nanotubes, boron nitride deserves a place in our consideration. Its properties differ, but in most ways, it meets the goal. It falls within our criteria. And so you may be asking yourself, is that it? Is there really only 3 things that we have to consider? Well, we don't really have any other options. Now, having said that, a longer answer is that we might have some other options. There are a number of theoretical structures, 3D graphenes, complexes of carbon and silicon, planar boron nitride derivatives, and very exotic carbon structures, graphines, where we've got alternating triple and single bonds. An example of one of those 3D structures is this pillared graphene on the right here. If one of these materials could be made, there's a lot of potential for this sort of application. It could have very high strength, it would have good stability, other interesting structural applications. And that just gets more and more true as we look at some of the carbon-silicon complexes, at the planar boron nitrides. But I said this was all in theory, in silico, computational. Most of these materials have not been demonstrated to even exist. Some of them, like this pillared graphene structure, there's debate about whether there is even a possible synthesis method to make this material. So, while I won't rule out these theoretical structures, they are so far away from being practical that even in the long time horizon we're looking at for our design, I think they're still too impractical and too far away from being useful to be considered. Now, that might change in 5 or 10 years. Research marches on, so it depends how long we've got until we deploy our space elevator. But from what I'm seeing today, carbon nanotubes and boron nitride nanotubes are probably our main contenders, and graphene and maybe conventional planar boron nitride, there may be some space to consider them. So is that it? Pick our favorite of the existing strong molecules that are relatively far along in the research? Well, we all know that's not true. If it was, I wouldn't be asking this question. So let's consider for a moment another novel material of exciting properties, carbon fiber. First discovered right around 1860 as a powdery carbon material. Eventually, about 10-15 years later, a few electrical applications came out. A few were published, a few were patented. Another 10 or 15 years passed and we actually started seeing some of those applications materialize. So 20 to 30 years after this was first discovered, we start to see some initial applications. Now, it was suspected early on that there might be some potential for strength applications. But it wasn't until the 1940s that we started to see something like that in the lab, where we could make a strong fiber, quality fiber. It took another 20 years to get that synthesis above the lab scale and into something that industry would consider, and another 10 years beyond that, the early 70s, before we started to see production of strength-based applications for carbon fiber. Today, it's in fairly common use. A lot of automobiles, a lot of airplanes, high-end sporting equipment, bicycles, tennis rackets, a number of other applications. So, roughly 150 years from discovery to common application. And further, the driver of research was electrical properties for the better part of the first 80 years of this development cycle. It was only after that we started looking at strength. I bring this up because it parallels what we expect to see and what we are seeing with carbon nanotubes and with boron nitride nanotubes. We found a molecule with exciting properties: tensile strength, conductivity, etc. From that, we've started to develop useful materials. Interestingly enough, in both cases, electrical materials are still driving the research for these. Their properties are very important for the semiconductor industry. They're very exciting for aerospace applications, where conductivity per weight becomes important. They're also interesting from sensing and chemical protection perspectives. So really, the electrochemistry is what's driving research. We've started to get some applications that use these materials out in the wild, but they're not strength applications. Strength research is piggybacking on the electrochemistry research, but because of that, it's moving much more slowly. And in the case of carbon nanotubes, we have seen large-scale deployment of carbon nanotubes. Powdery nanotubes are very common as catalyst supports in the chemical industry. But we need ordered nanotubes, for reasons we'll see shortly. And so right now, neither of our materials is produced at large scale. For me, the takeaways from this are twofold. One, we've seen this sort of design process before. We're seeing it again now. And so there are things we expect to see happen, targets to meet, develop applications, get funding, get patents, etc. And if we want to move this process along, we need to figure out a way to go from the step we're on to the next step. The other takeaway is that having the exciting molecule is not enough. It can take decades, it can take 100 years before you get that exciting molecule to do something useful. And so that, more than anything else, is what we need to be pushing right now. The sooner these molecules show useful practical applications, the sooner they'll get more research, the sooner there will be more exploration of these molecules, the sooner there will be more production, the sooner there will be efforts to find new applications. So we've got our exciting molecule. We need to bridge the gap from nano up to macro, and that means this microscale structure. Ordered microstructures for our anisotropic materials. I'll explain that one in the next slide or two. Good interfaces to connect our materials to other materials. Right now, both carbon nanotubes, graphene, and boron nitride, the very things that make them so attractive as molecules, also mean they don't interact very well with other molecules, even other nanotubes. We need to find a way to deal with that, get them to play nicely with each other. Once we've got that microscale figured out, not just in terms of what it needs to be, but how to make that microstructure happen, then we can start pushing for larger production. We know we can get production by the ton, but we need quality production by the ton. It's not enough to have a ton of nanotubes. They've got to be good tubes. They've got to be in the right structure. So let's talk a bit more about that microscale structure. Now we need an ordered microstructure because both carbon nanotubes and boron nitride, and to a lesser extent graphene, are all anisotropic materials. Now we're used to isotropic materials. Let's use conductivity as an example. Copper is isotropic. If I have a cube of copper and measure from the left face to the right face, its conductivity, it will have a certain value. If I then measure conductivity from the top face to the bottom face, I should get about that same value for conductivity. This is not true for our nanotubes. They're much better conductors along the long axis than they are across the short one. We see the same thing for strength. We see the reverse for local attraction. the side walls are much more attractive to each other than the end caps are, so on and so forth. So order is important. I want to emphasize exactly how anisotropic our materials are. Even if we set aside properties and look just at geometry, the length to width ratio of a carbon nanotube is on the order of 10,000, 100,000, 1,000,000 to 1. For comparison structure, if you picture an ear of corn growing on a corn stalk, if that corn stalk were about 150 kilometers high, but still keeping its same diameter, that's about the same length to width ratio we see with these nanotubes. Same thing with boron nitride. So we need to have order in our structure. Otherwise, we're going to be dealing with a much, much weaker material. And we need to keep that order. And that's where binding and cross-linking with other materials comes in. So that once we get that order in place, we can lock it in and keep it from changing. So what does this mean when we get to our making a practical material? Well, we're going to have some load-bearing phase. This is going to be our nanotubes. Carbon nanotube, boron nitride. This could be our graphene, if graphene turns out to be the way to go. This is the part of our material that is going to be bearing the weight, dealing with the tensile forces. So we want as much of this as possible. But even if we have everything well aligned, we need to hold all of these fibers together so that that force is distributed evenly across them. If we don't have something like that, all the force will get deposited on one or two or some subset of our fibers, and the others will bear no load. Those first few will break. That will cause another subset to load. Those might not be able to bear the load and break, causing a cascade failure. So we might have a material without this binder that theoretically should be able to support a weight, but isn't, because that weight won't be evenly distributed. So making sure of that distribution is where our matrix material comes in. Now we don't want a lot of this, just a few percent by mass, because it doesn't really contribute to the load bearing itself. It's fairly weak. What it does, though, is hold all of our tubes together so that they work as one instead of as individual fibers. So that matrix holds everything together and needs to do that under some fairly extreme conditions, which means we need to make sure that the nanotubes don't just pull free from that matrix. And that's where interface design comes in. Most likely, this means chemical bonds. So we're going to do a little bit of damage to our nanotubes, carbon, boron nitride, whichever they are. And this will cause each individual tube to be a little bit weaker. But as we've seen, the individual tubes are not the problem right now. They're pretty close to our expected maximum for tensile strength per weight. We can afford to give up a little bit of that strength in order to get the macro scale material up from that aramid line into the area that we need it to be for our space elevator. And that's where this interface comes in. We're not going to break every bond on the surface, just a few, just enough to couple the matrix and the load-bearing phase, which will lead to the load-bearing phase elements being coupled together. Put simply, this is a low-matrix composite. It's actually a fairly common design approach used in composites. Become a lot more popular these days as people have been faced with just this sort of application, where you've got one material that is almost what you need, but you need a little bit of some other material to deal with some property limitation that your initial material had. So while we haven't seen much of this work for carbon nanotubes or boron nitride or graphene, the basic approach for developing a low matrix composite, researching those interfaces, that's well known. So we don't have to reinvent the wheel here. We just have to use that same process to design the wheel for our application. So the last point here is our industrial scale, whether or not this is going to be practical to do at large production. So first off, boron nitride. It's a young material. We're starting to see research into volume production. There are some labs around the world that can produce kilograms a day. But right now, that production has a lot of impurities. It's primarily powdery material. We don't yet have an ordered or organized structure for it. And the work on strength is just beginning. So while we know the molecules are up to task, we don't know how we're going to bridge those molecules into that macro material. So I like boron nitride. Especially, I like its radiation resistance and its resistivity. So I want to keep an eye on this. It's got a lot of potential, but it lags a few years behind other research areas, other materials that we're also considering. And we've got graphene. So graphene, a little older material than boron nitride, but we've got some issues. It's very easy to induce serious defects, even in a carefully controlled synthesis, because of the way we make graphene. And because graphene just has that single layer and no way to stabilize that layer, each defect is potentially catastrophic, and it can only handle a very small amount of defects before its tensile strength or other properties drop off beyond the usable point. Far fewer defects in terms of a percentage of bonds than we would expect with nanotubes, whether they're boron nitride or carbon. We've also got issues with the flake boundaries. If we just stack graphene on top of each other, we get graphite, pencil lead, not known for its high tensile strength. If we try and bind the graphene together at flakes, at the flake edges, better, but now we've got a polycrystalline material. If we try and synthesize large quantities of graphene, the best approach is to do an area-based synthesis, where we take a big sheet of copper or nickel, load the surface with carbon at a high temperature, and then let that carbon crystallize out into graphene. As a matter of fact, that's not only the best method, that's the primary method of making large flakes of graphene these days. This does not scale well, because even as you increase the surface area to be square meters, hundreds of square meters, your thickness is still one atom. It takes a lot of square meters to get up to kilograms or even tons when you're starting with one atom thick. The best approach for scale-up really does require new production methods. There's been some interesting work done in the last few years on exfoliating graphene from graphite, so you can get the flakes in larger volumes by mass. And if you can figure out a way to organize those, then maybe. But frankly, I think graphene's got too many problems with scale-up to give us the mass we need for our application. In applications where surface area is more important, like touchscreens, like coatings, graphene's got a lot of potential. But I don't think it's quite where we need to be. Which brings us back to carbon nanotubes. We can already make them with few defects. We know how to stabilize these defects. Most nanotubes are actually what are called multi-walled nanotubes, so there will be multiple tubes nested within each other, kind of like matryoshka dolls. And these inner tubes will stabilize outer ones, even as they accumulate defects. So a nanotube can sustain a much higher amount of damage than we would expect intuitively before we see a significant drop-off in properties. We already talked about how they're self-healing. We can produce these in incredibly high purity. We've got approaches already that can produce by the ton. There are approaches that can do high quality ordered nanotubes by the kilogram. So while we're not yet to the building space elevator stage, we've already got demonstrated industrial capacity and multiple roadmaps for scaling up. So of the three, my pick is carbon nanotubes. I do think boron nitride has a place, especially for dealing with radiation and oxidation. Graphene, maybe as a protective coating, or as some sort of repair material, or in other devices, but I'm just not seeing that coming out of the research. So if I have to back a single horse, carbon nanotubes is it. Though I would expect to see some sort of composite with some other protective material, and boron nitride nanotubes do seem like a good fit for that. Which brings us to our last question. When will you get your tether? Well, this figure here is every real fiber strength measurement for carbon nanotube fibers from the literature since 2002. Now these are fibers, this is not individual molecules. So we've brought a bunch of molecules together, formed a thread or a sheet or something like that, and then measured that tensile strength. And we can see over time it's generally trending up. We've gone from a little bit below 1 gigapascal per gram per cubic centimeter up to some measurements that are as high as 6 or 7. There's a very recent measurement, which I haven't added to this plot, which is about 8. So we're making progress. This progress is in the lab, so we've got a ways yet before this gets to industry. But the lab is where we start. And right now, while the lab is not as far along as we'd like it to be, it's steadily increasing. That picture gets even better when we break down that previous chart by different material type. Our two main materials, carbon nanotube fiber composite, where we take a powdery material and make a composite from it, or CNT spun fibers. Certain types of nanotubes can be spun the same way you would spin like silk or wool. These two, we're seeing steady and significant increases over the last 15 years or so, and we are expecting that to continue apace. But equally promising, we see a few new approaches, liquid spinning and cross-linking spun fibers, which debut in the literature as some of the strongest material yet produced. And they've got a lot of development potential ahead of them. So I think the picture for our carbon nanotubes is actually pretty rosy. We've got a real chance of getting that molecule strength into a practical macro material, and we're making good progress towards it. We won't have it tomorrow, but it won't be very long. My best guess, we should get to about 25 gigapascals, which is above the plausible line, but below the ideal line, in about 20 years. Now that'll be, whether that will be lab or industry, plus or minus 3 to 4 years on that. So, call it 25 years in total before we have industrial production of our 25 gigapascal material. Now it's possible that in a few years I'm going to look foolish for saying that, because as we saw in the last chart, all it took was 1 or 2 breakthroughs to get something exceeding our best results. So, we may well be there before 20 years is up, but if we just extrapolate from where we are now, 20 years seems reasonable. I expect our tether to be a low matrix carbon nanotube polymer composite. I also expect other materials to show up in the tether design. Boron nitride nanotubes in particular, perhaps as protective coatings for ozone area or for in radiation belts. As far as covering that distance, we can't just wait. We need to act, to do things, to try and make these materials advance. So we need to do more research into the morphology of these nanotube materials. Because as we saw, morphology is where these properties come from. If we don't understand how to control that, how to adjust that, then all we've got is guess and check. Which isn't bad, but there's 100 variables in this process. Guess and check on 100 variables, you're talking thousands of years. I don't have that kind of time. We also need to work on CNT polymer interfaces. This is an area, again, where we know how to do this research, but we haven't done it yet. And then once we've got that, we need to look at scaling up from the pilot scale we're at right now, with a few small companies with small production facilities, up to production in the kilograms or tons per day. When we get there, that's when we'll have our space elevator tether. I'm optimistic. 20 to 30 years. Sooner, if we're lucky. Longer, if we're not. But I think we've got a good chance of beating the spread on this one. So that's all I have for my presentation today. I'd like to thank you for listening and for inviting me to speak. As you've probably gathered, this is one of my favorite subjects, so any chance to talk about it I am glad to be involved in. I guess now will be the time for questions. Thank you.